Okay, I think we're live. So, hello everybody, and welcome to this 85 verse the series of the Latin American webinars on physics. Today, I'm going to be the host of this very interesting webinar that is going to be given by Johannes Herms from the Technician University of Munich, and he's going to talk about antinuclei cosmic rays and the potentiality, the sources and the potential for discoveries. So for all the people that is following the webinar, please, you can ask questions using our YouTube chat system in your YouTube channel. And please, you have to be aware that there is a small delay between the live transmission that we are having using Zoom here between all the people in the webinar and what is showing us in YouTube. So please write a little bit in ahead your questions to Johannes to be able to ask them at the end of the webinar. So Johannes, whenever you want, you can start.
Excellent. Thank you very much, Roberto, for the kind introduction, and to all of you for the opportunity to talk to you. I'm very happy to take part in this project of bridging oceans and mountains with physics. So let's get right to it. I will talk to you about galactic cosmic rays and what we can learn from them for fundamental particle physics and how antinuclei fit into that picture. Galactic cosmic rays are energetic charged particles that are accelerated either by astrophysics in the vicinity of very violent events in our galaxy, or potentially by interesting particle physics. And once they're produced, their movement in the galaxy is governed by magnetic fields because space is mostly empty. So that again imprints more astrophysics onto these cosmic rays. Now, I'm a particle physicist and I'm interested in fundamental particle physics. So the fundamental question for me in doing astroparticle physics is, how can we separate the astro from the particle? And in the case of cosmic rays, this goes towards rare cosmic rays. Now, the one big difference between astrophysics and particle physics, one big difference is the baryon asymmetry of the universe. Astrophysics accelerates lots of cosmic rays from the baryon-dominated interstellar gas. So the cosmic rays that we get from that are lots of protons, some helium, some metals, but it's going to be dominated by baryons. On the other hand, particle physics, if you have enough energy, you can do pair production. So you can do antimatter-matter pairs in one-to-one correspondence. So that if you look at antimatter cosmic rays instead of baryon cosmic rays, you get a huge background suppression. So you can hope that you can look only maybe at the particle physics that you're interested in and not at the astrophysical background. So this plot here shows, for example, fluxes of protons and helium, and then of rarer cosmic rays of electrons, positrons, also antimatter, but lighter than antiprotons, so they're easier to produce. And then antiprotons. And you can see that just by looking at antiprotons instead of protons, you've got many orders of magnitude of background suppression. And one additional advantage compared to gamma rays is that charged cosmic rays accumulate in the galaxy. So the magnetic field of the galaxy confines them, and they take about 10 million years to escape. So if we're looking at rare events like dark matter annihilation, then there's also some signal enhancement from that. So in this talk, I will first talk a bit about cosmic rays to give you the basics and the context of what we're doing here. Then we are talking about sources of antimatter in cosmic rays, of antinuclei in cosmic rays, specifically, which is the main motivation in this whole topic, about dark matter and a bit about primordial black hole evaporation. Before, in the end, we can then look into the different antinuclei of antiprotons, antideuterons, and antihelium and see what they will tell us. Antiprotons have been measured to astounding precision recently, and there's much to learn from that. Antideuterons, there's a dedicated experimental program just for antideuterons underway. And then in the end, there's some very exciting hints about antihelium from the AMS experiment. So let's get right into it. We start with cosmic rays. The life of cosmic rays starts at birth. So for most of the galactic cosmic rays, that is at acceleration. And the agreed upon source of galactic cosmic rays is that an exploding star in a supernova creates a shock wave. The shock wave leaves the star and now it propagates through the interstellar gas, which you can see, for example, here in optical in the yellow shock wave. And at this shock wave in the interstellar plasma, what happens is what's called first order Fermi acceleration. So it's acceleration by a plasma shock wave. So acceleration not like on Earth with electric fields, but there's a stochastic acceleration around the shock. And this is the source of the ubiquitous power laws in cosmic rays that we see. And this process is so efficient that tens of % of the kinetic energy of the supernova can be dumped into accelerated cosmic rays and B-field turbulence. Evidence for this, or proof of this, has only recently been determined by looking at this supernova remnant and others, and seeing that there is a pion decay spectrum coming from there, which is evidence for the fast protons that hit interstellar gas there. Once they're produced, they escape into the galaxy. Now, this is a picture of a typical disk galaxy like ours. But if you look into at that using radio waves, what you see is this. It's a big synchrotron halo around the galaxy created by electrons that move in the magnetic field that are confined close to the galaxy and by being bent by the magnetic fields emit radio radiation. What we can infer from that is that there is a magnetic field that extends many kiloparsec above the disk of the galaxy and can diffusively confine cosmic rays like electrons there. And we can describe the movement of cosmic rays in this turbulent magnetic field by diffusion, with the diffusion coefficient that mostly depends on the rigidity R of the particle. Rigidity is how easy a particle is to bend by a magnetic field, so it's momentum over charge. And this is the interactions with the magnetic fields are the reason that we often use this quantity of rigidity to talk about cosmic ray spectra. Now there's other processes than just diffusion going on in the galaxy. So for example, the magnetic field is attached to the movement of the magnetized plasma. So if in the galaxy there is a convective wind that blows the plasma out from the disk, then the cosmic rays will be convected along with the magnetized plasma. Also, there might be acceleration happening there by random waves in the magnetized plasma. And of course, if you look at the upper picture, it's clear that there is also stuff, not just magnetic fields. So this interstellar gas can be in the way, and nuclear collisions can happen. Cosmic rays can lose energy by ionization or Coulomb energy losses. And all of that can be described by this diffusion convection equation for the flux of cosmic rays. So the time evolution of the flux density is source term from injection, for example, by the supernova remnants, or from dark matter for that matter, minus a loss term by hitting interstellar gas and being lost. Then there's the diffusion term, the convection term. Then we have a energy redistribution and reacceleration term, and some discontinuous losses. Now that's the differential equation. Now we just need to model our galaxy, or the geometry of our galaxy, in which this takes place. And what is often used is a two-zone diffusion model, where we have in green here the diffusive halo. Then it's the zone through which this magnetic field extends and in which the galactic cosmic rays are confined. And in the middle, there's a thin galactic disk with all the stars and the supernova remnants and the gas and the sun. Now, having defined all of these things, we can move on and calculate what should happen. So we look at a source and think, what kind of cosmic rays should this source accelerate? If it's a shock wave, then it will accelerate all the elements that are abundant in the interstellar gas, like protons and helium and carbon. There are some elements which are not abundant in the interstellar gas. So that's what this chart shows, that the open circles show the abundance in the solar system or the interstellar gas. And you see that helium and hydrogen are very abundant, and carbon, nitrogen, oxygen also, but lithium, beryllium, boron are not. Now the black circles show what we find in cosmic rays. And you can see that there's a large abundance of boron generated somewhere on the way. And we call these cosmic rays here secondary cosmic rays because they're not accelerated by the primary source, like proton and helium, but they must be created as a secondary product somewhere else. And they're created by carbon and oxygen and so on, hitting interstellar gas and fragmenting into smaller nuclei. So that during all of the propagation of a carbon nucleus, this boron to carbon ratio will record how often this carbon nuclei hit interstellar gas particles. And this is a very sensitive probe of galactic cosmic ray propagation. And we can measure that with our instruments by just dividing the carbon flux by the boron flux by the carbon flux. And that's what this plot shows here. And you can see that we have really precise measurements of this. And we can now use this to tune our models of propagation and see whether our models of propagation are any good. And different implementations of models of propagation, for example, are the very well-known Galprop code. There's also the Dragon code. Both are fully numerical. And then in this study, in my work, what we used were a semi-analytical two-zone diffusion model, which has recently also become available as a pre-implemented code for you to use, should you be interested. Of course, the galaxy is not the only thing that stands between a supernova remnant and us. There's also, so for cosmic rays to reach detectors on Earth, there's a few more obstacles to overcome. So the next one will be the solar system, the solar wind. So what happens here is that the solar wind carries the magnetic field of the sun outwards, and any cosmic ray that should reach us at Earth in the center eventually needs to propagate against this convective wind. And that shields us from some of the cosmic rays. For example, this can be seen here. This is cosmic rays recorded by Voyager as it leaves the solar system. This blue curve is low energy cosmic rays created by the sun, and they drop as Voyager leaves the termination shot. Whereas higher energy cosmic rays that come from the galaxy, they suddenly rise as Voyager leaves the solar system, which is again evidence that the solar wind shields some of the galactic cosmic rays. In the end, if you have this geometry of propagation versus convection and you approximate that as one-dimensional, just the radial part, you take the stationary approximation, so then, then you can approximate this by a force field so that you can effectively describe this as an energy loss, so that the kinetic energy of cosmic rays that we observe at Earth is just the interstellar one minus some force field potential. And there is some attenuation that comes with propagating against this force field. So the flux that we observe is also lower than the flux that would be observed in the interstellar medium. Of course, there are some caveats to this very simplified pictures. The real problem is three-dimensional. There's time evolution in the sun. This, in the end, leads to charge sign dependence, so that this solar modulation is not the same for protons as it is for antiprotons. But for the moment, and looking at larger energy cosmic rays, this should suffice. Finally, the last barrier is the Earth's magnetic field. So the magnetic field of the Earth, thankfully, shields us from most of the low energy cosmic rays. For experiments, if we want to look at low energy cosmic rays, of course, that's not so good. Also, the Earth's magnetic field extends far up into the atmosphere. So even if we have some low Earth orbit satellites, we're still influenced by this. What you can see here on the right is a map with the vertical rigidity cutoff, below which cosmic rays cannot propagate to the height of 50 kilometers. So if you want to look at cosmic rays of only 1 GeV energy, you'd better build your experiment at the pole. So that's just as context for why many of the experiments that we're looking at are either on satellites, which have an inclined orbit so that they also pass the areas with lower cutoffs, or high altitude balloon flights over the poles. So much for the life of cosmic rays, standard astrophysical cosmic rays from birth to detection at Earth. Now we're going to look into sources of antinuclei in cosmic rays, which is what we're actually interested in. The first one we already talked a bit about are these secondary cosmic rays, which come from some primary cosmic ray species I hitting an interstellar gas atom J and producing in a high energy particle physics process an antinucleon and some other things. In more maths, that can be written as the flux of primary cosmic rays hitting a density of interstellar gas atoms. And then we have to integrate over the differential cross-section of producing antinuclei in here. And we know the average density of gas in the galaxy. We can measure fluxes of primary cosmic rays, at least at our position of the Earth, and extrapolate from there. And these production cross-sections, for example, from proton hitting a proton going into an antiproton, we can measure that on Earth in our colliders. And then to calculate this, we can either use an analytical parameterization of the data, so some fit function to the data, or we can use a Monte Carlo generator, tune that to all of the data that we have, and then also use it here. This will be the main background towards all the interesting particle physics searches that we want to do, right? I'm interested not just in supernova remnants and galactic cosmic ray propagation and what's going on in the galaxy out there. No, the main motivation is dark matter. As all of you are probably aware, there's a set of observations from the length scales of the CMB to large-scale structures, to galaxy clusters, to individual galaxies that can all be explained with one new thing, which would be a new particle. A new particle that is collisionless and that is very slow and doesn't do a lot. And the simplest particle model for dark matter, the arguably simplest, is WIMP dark matter, weakly interacting massive particle dark matter, that is produced via freeze-out in the early universe, which means for this discussion that the measured abundance of dark matter today predicts the annihilation cross-section of what's the cross-section for annihilation when two dark matter particles hit each other. Now we know that in the center of the galaxy and all through the galaxy, in fact, there is lots of dark matter. We can infer that from the rotation curves and the movement of stars in our own galaxy. So we expect in this model production of high energy particles, possibly including antinuclei in our galaxy today. If we want to calculate the flux that comes from that, we need to get a bit more concrete. So, for example, this was in the dark matter annihilation picture. Of course, dark matter, there could also be decaying particles producing fast particles that also produce antiprotons and whatever fancy things. But in this WIMP picture, what's most interesting is annihilation into some high energy final state, like 2b quarks or W bosons. And these particles, of course, we're talking about astrophysics here, right? They are not stable. They decay very fast into other things. And if there's a hadronic channel here, then in the end, what we get are lots of protons, pions, gamma rays, antiprotons, possibly antideuterons. And the source term for that then looks like this. So we have the number density of dark matter squared times this annihilation cross-section, for which we have a theory expectation, times then the spectrum of antinuclei that are produced through for annihilation into a channel F like BB bar. The halo profile is reasonably fixed by stellar movement or by simulations. We take very often in studies of charged cosmic rays of antiprotons BB bar or WW as representative annihilation channels. And then for the analysis in the end, we take these, the annihilation cross-section or the decay rate as free parameters. And the spectra, of course, we cannot observe at Earth. We have, unfortunately, never seen dark matter annihilate on Earth. So we don't know what the spectrum is going to look like. Instead, what we do is we use all that we know from collider experiments and tune a Monte Carlo like Pythia to that. And that then tells us the spectrum of antinuclei that comes from this. And these look like this. So what is shown here in blue are the spectra, source spectra for BB bar final states, and in red is for WW final states. And for our purposes, what is important here is that all of these spectra are peaked at low energies. So in terms of rarity of observing these, it would be most promising to place a detector to build something that is sensitive to low energies. And on the other hand, the astrophysical backgrounds are these steep power laws that drop as energy to the minus 2, so they drop very steeply. So that actually in antiprotons, they tend to stand out against the astrophysical background, which goes like this at higher energies. Now, this is the biggest motivation for looking for antiprotons in terms of particle physics. But there's one more interesting source that I'm going to talk about now, which are primordial black holes. So that goes like this. In the early 70s, Stephen Hawking discovered that there's a possibility of forming tiny, or well, black holes of all kinds of sizes in the early universe by just statistical large density fluctuations or in phase transitions in the early universe. And their masses could be very small, so for example, for a primordial black hole of mass of 10 to the 13 gram, that's 1.5 femtometer size. Now, of course, as you would think, that's pretty tiny, right? So let's look into quantum effects. This prompted him to look into quantum effects of black holes, leading to the celebrated theoretical result that black holes should emit particles as if they were hot bodies with a temperature that can reach GeV if the mass is only small enough. 10 to the 13 gram is pretty small for astrophysical masses. So the sun is 10 to the 33 gram, I think. So this is a very, very tiny black hole. And this evaporation, emitting particles, leads to mass loss. So this black hole should in the end evaporate and vanish. And this result also predicts that if in the early universe black holes were formed with mass smaller than 5 times 10 to the 14 gram, they should have evaporated by now. Or for example, a black hole of the mass, if you have a black hole of mass 10 to the 13 grams, then it's already 1 GeV hot, and it will only last for 10,000 years until it's completely gone. Now, as I said, the emission is expected to look as if from a hot body. So the elementary particle emission rate from one primordial black hole or from one black hole looks like this. So just thermal here, depending on the spin of the particle that you're emitting, the energy of the particle and the temperature of the black hole. And here there's some gray body factor. So it's not a perfect black body, but there's this additional factor that comes from the fact that the black hole is in size comparable to the wavelength of the particle you're emitting. So that then in this picture, the black hole should emit, if it's very massive, only massless particles. So here, if it's very massive, the temperature is small, so the energy of the particle you're emitting also needs to be small. So only massless particles like gravitons, photons, maybe neutrinos should be emitted. But then as the black hole evaporates and the mass drops, the temperature grows, and as the temperature becomes large enough, also electrons and positrons and pions should be emitted. And as the temperature goes above lambda QCD, you expect emission to be described by emission of elementary quarks and gluons that then later hadronize into stable particles like maybe antiprotons. So we want to calculate what would the spectrum look like of antiprotons from primordial black holes. For that, of course, well, we have to, so for the spectrum of antinuclei from primordial black holes, we have to integrate here over the emission rate of elementary particles, quarks and gluons, that later hadronize into the antinuclei that we want to look at. So we have to multiply that by a fragmentation function of the initial particle radiated, like an up quark, fragmenting how many antiprotons do we get from that. Of course, we're not interested just in a single black hole, but we want to look at the spectrum that's emitted from all of the black holes in the galaxy. So we need some information about the black hole mass distribution that we have in the galaxy. So here on the left, if we take these two examples of what might be the initial mass distribution after formation of black holes, and they look like this. If we then take into account that these black holes lose mass, and the smaller the mass, the faster they lose their mass. This means that the spectrum evolves, and it evolves fastest for the lightest black holes. So for black holes that are smaller than this mass of black holes that has evaporated by now, there is a universal spectrum that we obtain just from this evaporation law, which is that the NDM should rise as m squared, quite independently of what complicated shapes the spectrum might look like. As long as it is kind of smooth around here, there is a universal spectrum, there's a universal mass distribution, mass function for black holes that can emit nuclei or antinuclei, so that have GeV temperatures. That means that we can calculate the primordial black hole source term without many assumptions on what the mass distribution of black holes actually looks like, by just taking what we had here, the single black hole spectrum, and folding that with this the NDM, which is just m squared. And in the end, what we get from that is a one-parameter spectrum. The only parameter here is the normalization. It is very predictive in the sense that the shape is completely fixed by primordial black hole evaporation plus this universal mass spectrum in the low mass primordial black hole range. So while maybe it's not as exciting as dark matter, it is a very interesting benchmark to look into and to compare data to. With that, we can actually look into the data. So now we're going to talk about experiments and observations and how to explain them. And a very big role here plays the instrument that has observed most cosmic ray antiprotons so far, which is the AMS-02 experiment that you can see here, which is on board of the International Space Station. So it's orbiting the Earth and at 100 kilometers high. And the idea is that cosmic rays come in from here and then hit all of the detector parts inside here, and then we can analyze that. This detector is built like that. So it's quite similar to the particle detectors that we used to in our collider experiments on Earth. So it has a tracker system, it has a magnet for deflection. So let's go through this from the incoming cosmic ray direction. So let's say there's a cosmic ray coming in here, it hits the tracker here Here, there's a transition radiation detector that is built to separate electrons from nuclei. Then it hits the inner part of the detector where there's a strong magnetic field, and it's deflected so that it leaves a track in the tracker from which we can reconstruct the particle's rigidity. It leaves the time of flight system, which is used for velocity determination if the particle is not too fast. And then here it hits the ring imaging Cherenkov detector, which is used for velocity determination if the particle is a bit faster. And in the bottom here, there's an electron calorimeter, which we're not interested in because this is a talk about antinuclei, not electrons. And the interesting thing here, and why it really changes all of these galactic cosmic ray discussions, is that they, for the first time, have percent-level precision for galactic cosmic rays over a large range in energies. So this, for example, is old results from 2015, but you can see that you cannot even see the error bars in the antiproton to proton ratio here. It's really a very precise measurement. So it's interesting to ask, is there anything exciting in there? And if you ask the AMS people if there's anything exciting, they will come up with something. So they always have something exciting. So if you compare the spectrum, it's the same as before, just here on a linear scale instead of a log scale. And compare that to the secondary expectation from some old paper, then you would conclude that, well, there's a huge gap here. What is happening? And of course, they also offer the explanation of what might be happening, right? There could be dark matter annihilating, which would be amazing. Now it turns out that if you really take into account also the other measurements that AMS did on the proton flux and the helium flux, then this secondary production line here is no longer tenable. But still, with these data, you can make very careful analyses, which these people here have done a few years ago. So what you can see here again is now this is the antiproton flux multiplied with some rigidity scaling here so that it's easier to see the shape. And it's very hard because the error bars to see anything in here because the error bars are so small. But what they find when they fit secondary production plus a possible dark matter component to this is this plot here on the right, where depending on the dark matter mass, you get limits on the dark matter annihilation cross-section, which here, this range here is for a different propagation model, so it kind of shows the uncertainty in propagation, which are much better than the gamma ray limits from that time. And excitingly, there is about a 3 sigma excess around here, which is very hard to see in this plot. But it's very clear that there is a 3 sigma excess, at least in this paper, here, which lies right at the thermal annihilation cross-section, which we expected all along, right, if we believed in the WIMP. So that's very exciting. Now, what's the status today? It's unfortunately not as simple. So because if you look at that, then you see that the signal is just 10–20% of the overall flux. So we are looking really into a precision measurement with cosmic rays. So that it's not that easy. And the picture today looks more like this. I took this slide from a workshop last week, actually, by Michael Kosmeier, so one of the authors of the previous slide, where he summarizes the recent developments on this antiproton excess, if you like. So there's been a few studies. The main thing is that AMS has not yet published any covariance matrices, any correlations between their errors. So theorists have tried hard to come up with their best guesses for what the correlation of the errors might be. That's one thing. Then you need to be really careful in accounting for the propagation errors. So in the previous study, they just used a few example realizations of the galaxy, for example, of propagation models. All of these guys here, they really scanned over propagation models and doing in many cases a joint fit of the boron to carbon ratio to constrain the propagation model, and then the antiproton to proton ratio. Another big thing is, and that's maybe best seen here in this lower right-hand plot. So in black, that's these are residuals to some best fit. But what you see is that the errors of the measurement are smaller than this green band by a factor of 2, something like that. And green is the cross-section uncertainty. The fact that we know too little about antiproton production to be able to predict the antiproton flux to the same accuracy as the experiment can measure. So now the Michael Kosmeyer and Fiorenzo Donato and other people have, people from this community here have initiated a push to measure more antiproton production cross-sections to be able to take more out of this measurement. And until then, well, so at the moment it looks a bit like there's 1.1 sigma, very nice limits, but no excess. To other people claiming there's maybe up to 4.7 sigma and a robust excess, which is also consistent with the Galactic Center GeV excess. So there is some excitement still around. And in the end, it will get settled by the experiment publishing their own error correlations would be one thing. And then better knowledge about antiproton production would really help this out. Or there is one other exciting option, which is to look at a channel that has less background, which is where antideuterons enter the game. So antideuterons are one antibaryon more. Now, if you look at the secondary production, what happens is mostly one proton hits another proton, produces, let's say, an antideuteron, and baryon number in here must be conserved, right? That means that in addition to the antideuteron, which has baryon number -2, if we start out with baryon number 2, we need to produce 4 more nucleons, so that the threshold energy in this process is 6 times the nucleon mass. And the threshold energy for an incoming cosmic ray proton needs to be 16 GeV, which is quite a lot already. So 3 times more than for antiproton production. That suppresses the background, of course, but there is this other effect that antideuterons or larger antinuclei like antihelium will always be produced boosted, because you need so much energy in this fixed target initial state. So there is some energy below which there cannot be antideuterons produced. And that gives a huge signal to background boost for low energy antinuclei. Because secondary production of antideuterons drops precipitously at low energies. So if you now look for dark matter, which we saw was peaked at low energies, here at these low energies, there's going to be almost no background if you look in antideuterons. Okay, so let's calculate how many antideuterons do we get. The problem is that antideuterons are quite rare, and the experimental data is not sufficient to get a data-driven differential antideuteron multiplicity for example, proton-proton collisions. So we have to do some phenomenology, some modeling. And the simplest model you can do is the factorized coalescence model, where you just say, well, okay, I look at my process, look at the antiproton multiplicity, and then let's see what's the probability, so to say, for an antiproton produced with this momentum and with this momentum, okay? And then there's this coalescence factor, some probability that these two antiproton and an antineutron will merge into an antideuteron. And this works, and so empirically this works well for high multiplicity processes. So for heavy ion collisions at the Large Hadron Collider, this can describe the data quite well. But it's quite clear that this will not work, for example, close to the antideutron production threshold, where the antiproton multiplicity doesn't know anything about the fact that we are really interested in only processes where 2 antinucleons are produced. So the next best thing that you can do is to do event-by-event coalescence, which is kind of state-of-the-art of how this is done, or used to be done, which is that we now generate lots of Monte Carlo events and look into those that have 2 antinucleons. So we run our Monte Carlo, let it do all of the hadronization and stuff, and then we look at all of the events that have 2 antinucleons. Now, if their momenta are aligned enough that, so the physical picture, that the binding energy of the antideuteron can overcome the momentum difference, so that their momenta are close enough, they're close enough in momentum space that the binding energy can overcome the difference, then they will merge into an antideuteron. This is obviously physically not a nice model because, well, we know there's quantum mechanics, and this sharp cutoff in momentum space has nothing quantum mechanical to it. So it fails on formal grounds already. So what in practice we do is we take this as a phenomenological model, as a one-parameter model for the differential antideuteron multiplicity. And we determine this coalescence momentum not from this theoretical hand-wavy argument with binding energies, but from data. And even then, it turns out that we have to allow for different coalescence momenta P0 for different processes, which kind of makes sense. So proton-proton collisions has lots of, at 7 TeV has a lot of hadrons, large multiplicity, many things going on. Far less clean than electron-electron collisions at 10 GeV. So doing this and then using the coalescence momentum that we determined from proton-proton collisions for the secondary background, which is mostly proton-proton collisions, and from cleaner, high-energy particle physics processes like clean processes like electron-positron annihilation for the dark matter process, or here Z decay for example, dark matter going into WW, it makes sense. It's kind of similar to Z decay. That's how we calculate our spectra in the end. Yeah, so recently there's been some nice developments on building a more quantum mechanical and maybe a physically more correct picture to this, but I don't have time to go into it. And in the end, this is what we get. Antideuteron prospects given the antiproton labels. So this top row of plots shows antiproton spectra for different secondary types. Then here black is always secondaries, so the astrophysical background. And these other lines are chosen large enough so that they're just compatible with the data plus secondaries. And you can see that all of the interesting the things that we're interested in, dark matter and primordial black holes, can only make up about order 10% of the flux. So in antiprotons, we really need to do a precision study if we want to learn anything about antideuterons. Anything about dark matter or primordial black holes. Whereas if you look at antideuterons, you can see that the secondary flux drops a lot towards low energies. Whereas the dark matter and primordial black hole flux is not affected by that. So if we build a detector that is sensitive to these kinds of fluxes, that would be, and then found antideuterons, that would be a very strong indication that there's something interesting going on here. Okay, so let's do that. There's actually an experiment planned and set to fly next year over Antarctica, which is the GAPS experiment. It's an Antarctic balloon mission and is specifically purpose-built for low-energy antinuclei. So it's built to have very good separation between antideuterons and antiprotons. And that works like this. So this, let's have an antideuteron coming in. And speed is measured in the time of flight detector here. And then there's a very thick target detector system in which the antideuteron is actually stopped and then forms an exotic atom, so the negative antideuteron with the silicon nucleus. As this exotic atom de-excites, it emits characteristic X-rays that are different between antiprotons and antideuterons. And then in the end, of course, you have the annihilation signal of the antideuteron actually eating up part of the silicon nucleus, from which we will get lots of pions. Many more than from an antiproton annihilating. So this is very exciting, and it might find something, and we will know in 2 years. Until then, we have some other exciting things to talk about if we want, although they are a bit more speculative, which brings me to Antihelium. There have been claims, but no published articles about Antihelium events being observed at the AMS-02 experiments. So this is an event display of an Antihelium candidate event, where they measure that it's a particle with charge -2 and mass 3.8 plus minus something. Yeah. So actually the mass is even more consistent with Antihelium-4 than Antihelium-3, which is very exciting and hard to believe. And the reason for that is like this. If we want to make predictions for Antihelium, we are in even more trouble than for antideuterons because there's even less data for Antihelium than for antideuterons. But the general trend is that this shows something like a normalized multiplicity for antinucleons of some mass number A. So this would be antiprotons. And then in the same type of collision observed at Alice, this would be antideuterons. This would be the Antihelium-3 multiplicity. And this is the Antihelium-4 multiplicity. And there is a factor of a few hundred for each antinucleon that you add. Now we have measured antiprotons, so we know how many antiprotons are out there. And for all of the components, for secondaries, for dark matter, for primordial black holes, all the particle things, if you want to produce some antihelium, you're going to produce lots more antiprotons in the process. And those we can compare to what we've seen. Yeah, so we can do the same exercise that we did for antideuterons. So taking the observed antiproton spectra, looking how much antideuterons can there be, and we can also look at how much antihelium can there be. And we did that for Antihelium-3, and this is the result. So here there's different secondary production of antihelium, and these are the maximal possible fluxes from dark matter without overshooting antiprotons. If dark matter annihilates into W bosons or B quarks, or here for primordial black holes. And what you see is that the projected AMS-02 18-year limit for the detection of antihelium is above all of these. Maybe, this uncertainty is related to the uncertainty in coalescence of antihelium, which is huge because we have so little data. It's really hard to make it work out for Antihelium-3. Most of the time, the observed antihelium flux is an order of magnitude, at least, above the secondary expectation. And even with dark matter, it's hard to make it work. Some other people who were made some much more conservative assumptions about antiprotons, they find that the antihelium flux, if these events by AMS are actually antihelium, then they would be marginally maybe compatible with a dark matter origin. But this event that we looked at 2 slides ago looked like Antihelium-4 and 2 sigma, something like that. So how is that going to work if particle production with particle physics processes with coalescence drop by a factor of a few hundred for every antinucleon that you add? So that's what these people here looked into. So here, this is a secondary prediction of Antihelium-3 and Antihelium-4 compared to the AMS 5-year sensitivity. So you can see that maybe if you're really, really good, if there's something that we really misunderstood about antihelium coalescence or galactic cosmic rays, then maybe you can make this intersect here, maybe. But there's no way then there's a secondary antihelium flux that can be detected at these rates. And that holds true for all of the particle physics processes where you produce the antinucleus by coalescence. Of course, if you ask, well, if you put it to a dark matter phenomenologist, it's impossible that dark matter can do this, then a good phenomenologist will come up with a model that does it, even if it looks very strange. Now, if we took these antihelium-4 events for granted, this would mean either some extremely involved, complex, really odd dark matter model, or it would mean that there is antihelium somewhere in our galaxy, that there are antimatter regions in our galaxy, either as clouds or as compact antimatter objects. That would be a very extreme conclusion, and the kind of evidence that AMS has until now is in no way sufficient to support that. But it's not unheard of in theory. So there's been, for example, this paper of baryogenesis, which predicts a small fraction of the mass density of the universe to be in the form of compact antibaryonic regions. So though extreme, it's not impossible. Yeah, this brings me to my conclusions and summary. We talked about antinuclei in cosmic rays, why they are a very promising detection channel for exotic particle physics in the galaxy, first and foremost, dark matter annihilation. We looked into the state of the art of what's going on in antiprotons. Antiprotons place competitive limits on WIMP annihilation, but the secondary background limits the discovery potential. So it's really hard to convince a seasoned particle physicist that what you find there is actually particle physics and not just some astro. But for antideuterons, there's the promise that the secondary background would be orders of magnitude lower, so that even with nothing visible in antiprotons, low-energy antideuterons may harbor signals from dark matter annihilation, orders of magnitude above the secondary background. And in the end, there was a fun excursion about antihelium events at AMS-02 and what they would, if true, imply about the universe we live in. Thank you very much for your attention, and I look forward to questions.
Thank you very much, Johannes. It was very interesting webinar, your talk. In fact, it was very interesting listening because it's from my area. So let's start with for the people that is in YouTube, please start to write your question, because you know there is a small delay between what we are living here inside the Zoom session and what you see in YouTube. So for the moment, we're going to start with the question from the same people that are here in the Zoom session. I don't know if some of the other coordinators want to start with the first question. No, anyway, I have many.
I have a question.
Nicolas.
So thanks first for the super nice talk. If you go to, I think it was the slide number 14 or 15, I'm not sure. You show the spectrum for the antideuterons.
This here?
No, I think it was previous one or after.
Antideuterons from where? Dark matter, or is it?
That one. Yes, exactly, from dark matter. So for instance, in the 10 GeV in the right-hand side, so you have like this peak at exactly that. So what's that?
Yeah, so in the B quark, there's always, in the B quark channel, what you can form is you can form a B meson. So all of the low energy tail here is just from, for example, the strength fragmentation of your quark jet. But for the specific case of the B quarks, there's always some additional stuff from the leading quark, so to say. And that's what gives you this peak and this peak here, and also this peak here.
That's D.
Yeah.
Matter D source. Okay. I see.
Yeah, so if we're looking into light quark spectra, then that should be absent.
Okay, yeah. Thank you.
So another question. Johannes, I have a question about about the coalescence factor. Do you know if there are other models than the one that you presented? Because since it's rather simple trying to, because there are no data, as you said.
Yeah.
But
so the biggest problem is that if you don't have lots of data, then whatever model you make must not be very complex, because you cannot determine so many parameters from the data. Nevertheless, it should capture the relevant physics so that you trust it where you don't have data, which is the whole point of the model, right? And for this factorized coalescence model, the simplest thing you can do, it's been investigated where it fails, and that's the reason why people today mostly use event-by-event coalescence. So as you say, this classical description is not very trustworthy. So recently, there's been some developments. So this model here can be made totally fine, or there's been some developments on starting with heavy ion collisions by Bloom and others, and determining the coalescence factor there, and then using some arguments to extend the model from here, from the case where it works to also the other ones. But for me, the most exciting one is these recent developments where they actually do a quantum mechanical description of coalescence. So what they do is they use Monte Carlo to determine the distribution of protons and antiprotons and antineutrons. And they calculate the two-particle wave functions from there, and then project them onto an antideuteron bound state, which is what you would do, right? So that sounds like a sensible quantum mechanical description of what should be going on. Yeah. And then they came up with a nice Wigner function-based approach in which you can use Monte Carlo to take care of the correlations between antiprotons and antineutrons that you have, and characterize them, and then analytically do the quantum mechanical part of projecting that onto the bound state. Yeah. And that looks very promising, though so far it hasn't been tested on low energy data. So to me, it's not clear yet whether it also works close to threshold, but I hope it would, because it looks like a much more sensible model than what came before.
Yeah, more realistic.
Kind of ahead of the state of the art at the moment.
Yeah. So, but in that sense, one question related with this, because since we know so few about this coalescence factor, the coalescence momentum, it could be also a possibility that there are kind of resonance in this coalescence factor that make more feasible to, in some production processes, you coalescence more than in others. For instance, what we can see here in the same table that you're presenting, that for low energy, you have much smaller coalescence momenta, and for high energy, using just PT tune coalescence momentum, because also it's very big, the spread between Monte Carlos.
Yeah, that's possible. So what that effectively would correspond to is that now at the moment, so for example, in this simple event-by-event coalescence model, there's this sharp cutoff. So there's 100% probability to merge at very low momentum separation, and then it drops to zero abruptly. And what you would suggest is that there might be something where maybe at low relative momenta, there's a large probability to merge, and maybe then there's a resonance later.
Maybe,
larger momentum. Yeah,
that it happens with the B meson production, like when there is the resonant, you produce more antideuteron, so on. So yeah, or antiprotons also, because this B meson is everywhere, especially at low energy.
Yeah. So the coalescence modeling is the weak point of anything involving antideuterons. So antideuterons, you cannot really use them to put constraints on dark matter, because we don't really know how much we expect of antideuterons. But the other way around, it works, that we say if we find antideuterons, then they cannot come from secondaries. or if we find antideuterons at at this level, for example, then we can be quite sure, because there's orders of magnitude in between here, that it's not secondaries. So that way around it works. It's more of a detection channel, not so much a constraints channel.
So a small curiosity, how large is the uncertainty, I mean, the impact of the coalescent momentum in the flux? Is it like square power of 2 or power of 3 of the...
It goes as the third power. Okay. So to say about like the volume in momentum space of a ball within which all the momenta coalesce. And here there's about, depending on the process, maybe you can take there's a factor of 2 or even more of uncertainties. So that gives you a factor of 10. Mm-hmm. It's a huge,
okay. So that is very important for the to establish some constraints. Yeah. And I mean, I have more questions, but I'm gonna let the other people to ask. I don't know if the other guys here in the and also in YouTube, you still have time to make some questions. I don't know. Okay, so because I'm very interested in this coalescence function, because it's the key part of the production of antideuteron. But for instance, have you tried, or other people have, since you have read more about this, I mean, and you're working on that, to try to use the same coalescent factor or coalescent model for the production of deuterium? I mean, since it should be more abundant in, I mean, it's more messy, the signal, but, or is it expected that it's symmetrical? You can form deuterium in the same way that you form antideuterium. I mean, starting from a proton proton neutron, proton antiproton neutron, just the same coalescent function, or
for high energy collisions like at Alice, the experimental result is that it's pretty much equal. So the antideuteron to deuteron ratio, if you have 70 the proton-proton collisions, is pretty much 1. Mm-hmm. So for that, you then also infer the same coalescence parameter. But the problem is that, so for using this with lower energy processes, where it's not clear that so for proton-proton collisions at smaller energies where it's not clear that it should be symmetric, it's unclear how much we can learn from that, because we anyway have this really big process dependence here. So what is done at the moment is to calculate the secondary production. You use the measurement of the P0 that you infer from proton-proton collisions. And for production from dark matter, you use the one that you infer from Z decay or from leptonic processes.
Yeah, because they are more cleaner.
But using one production is not clear how that would help. But of course, I mean, I'm pretty sure that the people here for the plus E minus, where there's no baryon number involved in the initial state, I'm sure that for the determination of the P0, they took into account deuterons and antideuterons.
Okay, one more question that I have, but not about coalescence, because it's a bit too much question about that. Have you? I don't know if you didn't present, or maybe you didn't. You are exploring also the case of decaying dark matter, because in that sense you don't have the restriction because of the annihilation cross section of the WIMP particle. Is it feasible to observe this kind of processes in AMS, for instance, than in?
So the thing is that the only thing that really changes between annihilating dark matter and decaying dark matter is the spatial distribution of sources. So annihilating dark matter is proportional to the dark matter density squared, so it's more peaked towards the center of the galaxy. Decaying dark matter has a gentler slope because it's only proportional to the number density. But the spectrum is going to look the same. And in our analysis, we treat the annihilation cross-section and the decay rate as 3 parameters anyway.
Oh, okay.
So the normalization of this is basically limited or fixed by antiprotons. So the results for what you could get in antideuterons are basically the same. And also that also implies that all of these fancy these limits here on dark matter annihilation can be pretty easily recast into limits on dark matter decay. Because of this diffusive process in galactic cosmic ray propagation, the different density, the different source profiles for annihilation and decay don't matter much. They do not influence the spectrum a lot. So you can practically directly translate this into a limit on dark matter decay.
Okay, I got it. So I'm going to check YouTube for question for Johannes. It seems there are not questions here in YouTube. So for the people that is following this transmission, please, you still have time. I don't know, people here from the Zoom session. If you have questions, you can unmute yourself and ask the question to Johannes. And also. Also I have a question.
Yes, I did. Sorry.
Okay.
So I'm gonna go for it. I was hesitating because I think a previous speaker mentioned the excess that you were mentioning before, and discussed the dark matter explanation for this. And I think I asked the same question at that time, but I'm going to do it again because I remember the answer. So the question was, if dark matter direct detection, the bounds have an effect in the possible explanation of dark matter as a source of the excess, in case the excess is there. In the case of decaying dark matter, of course, there's no issue, right? But in the case of its co-annihilating, I was wondering if there's anything coming from the direct search bounds.
Yeah, so as soon as you specify a model, yes. So if you have a model of dark matter, say it's I don't know, some real scalar thing in dark matter by the Higgs portal, then you can calculate correlations. But if you don't have a model, then it's possible that the particle physics, well, it depends on the on your more detailed model. So if you can have dark matter direct detection suppressed by some velocity dependent operators, by different couplings to the quarks. Whereas the annihilation is always kind of fixed by production, right? As long as you have WIMP dark matter, there is a quite clear prediction, except for the final state of the annihilation, of what the annihilation rate should be. Now, for the dark matter direct detection, there is no such clear prediction, depending on the model. If it's a simple contact interaction, which again would be a model, then there would be a prediction. And then typically direct detection bounds are very strong.
Right, so if we have like a neutralino dark matter or something like this, I mean, would that be able to avoid bounds and explain it simultaneously? For instance, I don't know, I'm just...
Yeah. I really don't know much about neutralino dark matter.
Just came in from...
You could imagine it. I think you can suppress... So now we're talking about dark matter direct detection, right? How can you suppress dark matter direct detection to comply with bounds? Mostly. Mm-hmm. Because the annihilation cross-section
the
annihilation cross-section is going to be close to the thermal one. Okay, unless you do co-annihilation. But I would... I'm really out of my field here, but I guess maybe if you have the dark matter annihilation on the Higgs resonance, then the annihilation cross-section today would be the same as in the early universe, but the dark matter direct detection points could be suppressed because you have tiny couplings.
Sure.
So I'm sure there can be examples. Yeah.
Okay. Great. Thank you very much.
So yeah, I was muted, sorry. So I guess I don't know, for the people here and also in YouTube, there are no more questions. So I guess it's a good time to finish the webinar. So first of all, I want to thank you, Johannes, because of your talk. That was very interesting. Indeed, I like it a lot, the slides.
Thank you very much.
Take it for especially for all the references. There are many references that I was looking in the past, but I couldn't find when they were in the first part of the introduction. And for all the work that you have done, also for that you're doing your PhD and so on. So thank you, Johannes. Thank you all the people that participated of the webinar and all our viewers in YouTube. And in 2 weeks, we're gonna have Oscar Vives, sorry, from the University of Valencia, that he will give also a webinar. So for all the rest, have a good weekend and so on. See you on the next time.
Thank you very much.